So we'll start section 1.2, which deals with analyzing graphs of functions. And we'll talk about a couple of topics. One of those is estimating function values. So in other words, I have a graph here, and let's call this graph f of x. So you might be asked questions like, just kind of put a box here, what is the value of f of 2, right? Well, basically that is telling you that x is equal to 2. And your job is to find out what y is at that time. Okay? So, that being said, right, let's actually give some numbers, let's give some depth to this graph here a little bit. So, let's say we just did something like that, right? So if I said what's f of 2, I'm thinking that has a value of -2 according to this picture. If somebody said, hey, what is f of -3? Right? Well, when x is -3, y is equal to 0. Right? Now, let's take a look at another idea, right? What if somebody says, where is f of x equal to 2, right? We just have to understand now at this point that this is their way of saying, well, now y is equal to 2. So what is x? And so again, if we look very carefully, when y is equal to 2, right, that could be any one of these places right here. Boom, boom, or let's say right around here. So you could actually have 3 different answers there. It could be x equals, let's say somewhere in the -2 range. Again, we're estimating, right? 0 would be another x value, and then again maybe at 3. So the big takeaway from this graph is understanding notationally whether they're asking me for a value that represents a y-coordinate or one that represents an x-coordinate. Okay, now domain and range, right? How do we do that when we're looking at a graph? So basically, again, we're going to draw you something here. Let's kind of just end this right there. Right? Here's what our thought process is. When we look at domain, the traditional understanding is that domain is the set of all the x-coordinates of a relation, right? But the problem is, I don't know if anybody understands that when it comes to a graph. So when we look at a graph, if we are truly talking about x versus y, domain versus range, then the domain I would actually think of visually as all the x values spanned on the graph horizontally. So think left to right. I think that's the way I would go here, right? Whereas range, right? The range, again, most people are used to saying that has something to do with the y's, right? So I like to think of the range as all the values spanned when you go from low to high. So think low all the way up to high, right? So let's give this graph some numbers here. Let's just make it simple. Let's make that go out to 6. So at the -6 here. Right? Now, if I take a look at the domain, right, it looks like, let's use a different color here, it looks like the domain starts on this graph at -6 and it ends at 6. And when we kind of look wall to wall, it looks like the graph spans from -6 to 6. And the range, it looks like, goes from a low of -5, right, all the way up to a high of 4. Now you notice I'm using brackets here to describe this, right? Remember, we use brackets when we include numbers, but we use parentheses when we do not include numbers. So that would be akin to like open circle versus closed circle kind of thing. What would happen, this is a hypothetical situation here, right? What would happen if on the end of one of these graphs, let's say I saw an arrow, right? Well, that would change my domain and my range to include some infinity values. So I'll just put over here, with an arrow, right, the domain would actually go from -infinity, we assume it goes all the way to the left here, up until 6. Infinities never get a bracket because you can't actually land on infinity. And the range for this particular example would still be from -5, but now you can't cap it off at 4. You got to go all the way to infinity because of that arrow. All right, let's look at intercepts, right? So you have basically an x-intercept and a y-intercept. Right, you have the potential for that on any graph, right? There is another name we use for the x-intercept, and that's called the zero. So if you're ever asked to find the zero of a function, you're really just being asked to find the x-intercepts. So, staying with some graphs here. All right, let's highlight these points. So we have a y-intercept here, got a couple x-intercepts. If you're looking at a function, you can only have y-intercept. If it's not a function, that's you can't have more than one y-intercept. So let's just label these A, B, and C, and then D, right? So your x-intercepts here would be A, B, and C, your zeros along the x-axis, whereas your y-intercept would be D. What's a more appropriate way to say these? Well, usually it would be A, 0, B, 0, C, 0. Now again, these could be numbers, so -4, -2, and 8, or something of that nature. And then y-intercept you would express as 0, whatever the value is. All right, and finally in 1.2 we hit on a little bit of symmetry and whether functions are even or odd, and it's actually pretty simple. If a function is even, then it will have y-axis symmetry, and we'll explain what that means in a second. If a function is odd, it will have origin symmetry. So, let's take a look now at an example, right? Let's suppose that y is equal to, let's say x to the 4th minus 3x squared, right? So to test these kinds of things, what we're going to do is we'll first start for even by replacing all the x's with negative x's. And if we do that and it comes out to be the exact same equation that we started with, then we know that the function is even because it has y-axis symmetry. So when I do that here, just kind of think about this, right? If I put a negative in for x and raise it to the 4th power, put a negative in for x raised to the 2nd power, multiplied by 3, yeah, the negatives will go away, and so you literally will have the exact same thing. So it is definitely even. Now, by contrast, right, if you were looking at an odd function, we need to find out that when we plug in a negative value for x, we actually get -1 times f of x. So that would not happen with this previous example I did, but let me show you an example of where it might. All right, let's suppose we had y equals x to the 3rd plus x, right? So what I would do in a case like this is I would replace all the x's with a negative x, simplify and see what I get, and I get -x cubed minus x. Well, it just so happens that if you had taken a negative and then multiplied it by the original function, you would get what we just obtained by performing this symmetry test, right? So because you have that, you have origin symmetry, and that's what creates a function that is odd. Okay? So you notice the one symmetry test that we don't talk about is x-axis, and that's pretty standard. And that does not really have anything to do with whether or not a function is even or odd. So if something is even, remember it has y-axis symmetry, and if it is odd, it has origin symmetry. Now at this point, I think what you want to do is go into section 1.2, try some of those practice problems, and see how you do from there.